Y7 Current and Resistance. We first consider current density. You must be familiar with current. Current I is amount of charge passing through a cross-sectional area during the time interval delta t. We would like to express this current as an integral. You should be familiar with the flux that we learned in the last semester when we study fluid mechanics. It is very similar to that. In that case, we consider the flow of mass instead of flow of electric charge. Now we consider flow of electric charge. To simplify our analysis, we assume that every charged particles are identical to each other. So we have a single charge small q, and that is filling the space. The volume is V. And inside the volume V, we assume that there are n particles. And the capital N divided by V is called number density. If I multiply charge Q of each particle, what I would get in the numerator is the capital Q, that is the net charge inside the volume V. So Q divided by V should be the charge density, rho. This rho is the charge divided by volume, that is charge density. If I multiply this charge density, that is number density times the electric charge of each particle, multiplied by velocity, we assume that every particle is moving with the same magnitude and same direction to simplify our analysis. If I multiply, then we would get capital J, that is called current density. In fact, current density multiplied by the cross-sectional area as a scalar product, where the area becomes an area vector, then we can find J dot A, a vector that is a J times A times cosine theta, where the theta is the angle between the normal vector of a cross-sectional area with the area A, and the scalar product between them will give the cosine theta, where this theta is the angle between the normal vector of the cross-sectional plane and current density, and it becomes current. Let's see on the next page. We are familiar with computing the volume of this parallel pipe. You learned triple scalar product. A cross B is directed to the normal direction relative to the plane spanned by two vectors A and B. You will find the angle theta. That theta is the angle between the C, side vector C, and the normal vector with respect to the plane spanned by A and B. If theta becomes 90 degrees, that means C rotates about in this way, then A, B, C are coplanar. Then its volume becomes 0. When it reaches theta becomes 0 with an equal magnitude of C, in that case, this volume is maximized because of the scalar product between A cross B and C. And you know, in general, regardless of the directions of A, B, and C, the volume of this parallel pipe can always evaluate it in such a manner. Okay? Sometimes you would get a negative sign on it depending on the orientation. So you have to be careful about the sign, except that the absolute value of a triple scalar product represents the volume of the parallel pipe. When you compute A cross B, you have encountered a vector, this vector, A cross B. This vector represents area S spanned by two vectors, area of a parallelogram generated by two vectors. And this small n hat represents the unit vector perpendicular to this plane. Therefore, the area of a base and height is actually this absolute value of C, and cosine theta will be the volume of the parallel pipe. So now you understand clearly. So let's derive current from the information of current density and area vector. We recall number density, that is a number of charged particle inside the volume. And we multiply N by Q, then it becomes rho, that is the charge density. And if you multiply rho by the velocity of every particle, you will find current density. So this is a picture taken at time t, and this is a picture taken at time t plus dt. We assume every particle is moving with the same velocity. Because of that, there's a flow of a charge coming in, and it passes through a cross-sectional area whose magnitude is A, and it is something like n hat A, and n hat is the unit normal vector of the cross-sectional area. Because every particle is moving with the velocity v, the distance of travel at this point, this guy, this particle in front, this guy travels to reach this point. And the distance of travel is v dt, and the displacement vector, the x, must be v multiplied by the time difference dt. Because we have a surface area S, A, and it's a normal vector n hat, the volume of this parallel pipe, this is actually the rectangular pipe, it is just S, A times V dt. This is the n hat multiplied by change in this dV is the volume of this part spent by the current, charged current during the time dt. All right. We have NQ, that is charge density. Then dQ is the charge density multiplied by volume. So amount of charge contained inside this volume is dQ. And we have found that this dx can be expressed in terms of v dt. And why don't we combine NQ with V? Then we recall the definition of the current density. What is the current density? J equals rho V, and rho V is NQV. So we have NQ and V. That is the current density J. And dx become separated into v dt, and we remember this area vector whose magnitude is area and the normal parallel to the normal vector. If I combine them together, it becomes A is nothing but the integral of a differential area element. This is a small, this sigma, and we add them up to find out the integral, and this integral is nothing but the normal vector to this plane and multiplied by the area. So while we find the amount of charge contained inside this volume is J scalar product area vector, differential area vector, integrated over this surface and multiplied by dt. We divide both sides by dt, then you will get this one will be erased and the dq over dt, and you know very well this is the current. So finally, we have reached this point. Current can be always computed by integrating the current density over surface with the scalar product, where the sigma is the differential, the sigma vector is a vector whose magnitude is the area of this small surface, and n hat is the unit vector that is perpendicular to this surface. So you have to remember it very well. So this is a simple application of a previous problem. So please practice with the elementary problem. Here we have a flow of charged particle. They are in array, and we have equal uniform distribution of particles, and they are all flying along the z-axis. There is a cylinder. A cylinder has some angle with respect to the z-axis that is parallel to the velocity of each particle. We remember the current density is rho times v, and rho is a number density multiplied by its charge, and velocity is the speed multiplied by the unit vector along the z-axis. We recall that a unit vector that is making an angle theta with respect to the z-axis, and that is called the polar angle. And if this vector makes an angle, what kind of angle? Azimuthal angle on the xy plane, phi, then the unit vector is always expressed in such a manner. So in this case, we want to compute the various things. Surface area element of the upper lid, this upper lid, okay. And this radius is r. So you have to find a normal vector, and it is written in here. And what is the area? Pi r squared. So the surface area element of the upper lid is area multiplied by the unit normal vector. That's it. Current passing upper lid. There is an upper lid. We have a current density J that is a constant. It is along the z-axis. The magnitude is nqv, nqv, copy. This is constant, a unit vector. What we have to do is integrate J dot d sigma, and this d sigma is a trivial. Integral d sigma here is nothing but this vector, pi r squared and hat. The question is now J dot area vector, and this one is already obtained, but there is an angle between E3 hat and N hat. E3 hat dot N hat dot E3 hat. This one, there are typos. This is 1, this is 2, and this is 3. That's fine, right? This must be x-axis, y-axis, and z-axis. So 1, 2, 3. So if I multiply E3 hat as a scalar product, what I would get is a cosine theta only. So trivial problem. Charge carriers. If we have a charge Q moving along the direction with the velocity v, it will produce the current density nqv. Consider a very similar situation, except that charge q is replaced with minus q, and velocity of each charged particle is replaced with minus v. Then we have minus 1 squared, that is plus 1. Therefore, positive charge flow and negative charge flow against it with the same magnitude, but opposite direction and opposite charge. We do not have any difference between the two situations. So that's the one of the reason why we made a mistake. Benjamin Franklin made a mistake that current flows, that he fixed a positive charge that is opposite to the actual charge carrier. Now it is called electron. You must be familiar with SI units for the current, and this is a charge time current. You should also be familiar with the SI unit for power, that is work done per unit time. Okay, continuity equation, we learned this one in previous semester, but let us summarize this. A current passing through a closed surface is represented by the continuity equation. Perhaps when we learn fluid dynamics, we only consider a constant current density case in most cases, but this is a general expression for current continuity equation. It looks complicated, but it's very simple. Current flows, so amount of current coming in, passing through this surface, and amount of current passing out. You know, normal vector in here, current is this direction. So we have negative sign for J dot d sigma. On this surface, current enters. So there is increment of charge. In case the current flows out, J dot d sigma is a positive, and you will lose electric charge, lose gain. So gain is positive, you lose negative sum. If sum is positive, what happens? If charged flow comes out everywhere, then this one will result in the loss in the electric charge inside the container. That's the reason why on the closed surface, current density is evaluated, then you will find the change in the electric charge, and you need to put a negative sign on it, because flowing out of an electric current from inside, that results in the loss of the electric charge. In fact, this one can always expressed in terms of volume integral. Charge is the volume integral of density. And we know how to convert this one as a volume integral. This is the consequence of divergence theorem. Therefore, if we equate this one, this left-hand side is replaced with the volume integral, and right-hand side is also replaced with the volume integral, then you will result in a differential equation that is called the differential form of a continuity equation. Divergence J must be the same as the negative of the partial time derivative of charge density. So this represents current conservation when the net charge inside the container doesn't change. You mean rho is independent of time. That is a steady state, steady, independent of time. In that case, this one disappears. In that case, flow in, flow out, the amount, their amounts are the same, but opposite direction, they cancel. So the amount of charge contained inside the container is always the same. So mostly when you learn fluid dynamics, you consider these trivial problems only. Another example of this current conservation is when you study fluid dynamics, flow in, flow out across a small area and wide area. The amount of charge entering into surface, amount of charge leaving out of this surface should be the same to keep the net charge inside this funnel-shaped container is the same. So equals 0 means this situation. This is interesting, but an ideal case when inside the circuit, if there is a loop and there is no limitation of the flow, then whatever velocity it may acquire, it doesn't matter, because inside the amount of current forward and backward, they always cancel. So regardless of this velocity inside, uniform entering, uniform leaving, then the charge can be conserved. So this is an interesting mathematical problem. Resistor. Once you have an electric field, charged particle would accelerate. However, in actual situation inside a wire, unless it is absolute temperature 0, heavy particles are distributed over the space, and electron, actually the electron that is moving opposite direction, the accelerated charged particle hits the target particles and they lose their energy, and acceleration stops. But at some moment, due to the electric field, it accelerates again, and there is a multiple collision happen inside a wire. So the work done by the electric field results in the increase in the kinetic energy of a charged particle, but because of the many collisions with the heavy particles, it loses its own kinetic energy. That results in the kinetic energy of a heavy particle that doesn't move. Then, as a result, wire becomes hot. It's called Joule heating. And in addition, if you something pull under gravitation, usually particles accelerate, but it is impossible to have infinite velocity. Just like a parachute, it would reach a terminal velocity. That is the similar situation in here. Where is the gravitational potential energy? It is lost due to the collision with air molecules. So it will be a very tiny amount in the air case with the parachute. In this case, it can be extremely hot. So in some case, a fire breaks. Resistance and resistivity. Current density, electric field, they are proportional to each other inside a wire, and the constant coefficient depending on the material are called resistivity and conductivity. And in middle school, we made use of this kind of one to find out the actual resistance of a resistor if a geometry of the resistor is given. So I believe that you can do this calculation very well because you studied it in middle school. Sure, Ohm's law, it is just a review. You must know it very well. Let me pass. Mean free path. We considered this one in previous semester when we learned the statistical physics. So let me pass. I assume you understand the basic idea of a mean free path. Power is the work per unit time, and power is, you can compute the power potential difference multiplied by charge. If the potential difference is fixed, multiplied by charge is the work, and you divide this one by time, it becomes a current. So I times V is the work done by the electric field under the charge electrostatic potential difference V. And if you make use of Ohm's law, V equals IR, you can replace this one in terms I square R or V square over R. So this is the one of the reason why we use very high potential difference, even much larger than this, to transmit power. That saves a lot of energy. Transmission tower, very high. We have a very large, instead of 220, we have a very large potential difference to save our energy when it is being transmitted. 10 minutes break.